Right now, somewhere over the western Pacific Ocean, the atmosphere is doing something that should terrify you. Not in a distant, abstract, scientific paper kind of way. In the immediate, right now, this is actually happening kind of way that most news coverage of this event has completely failed to convey. A storm is out there. A storm that, by every meteorological metric we use to classify such things, has crossed from the category of severe weather event into something that deserves a different vocabulary entirely. Wind speeds that exceed the threshold of Category 5, the highest classification on the Saffir-Simpson scale, the level at which the scale essentially gives up trying to describe the destruction in gradations because everything above it is simply catastrophic. A central pressure that has dropped so fast, so dramatically, in such a compressed window of time that the meteorologists watching it in real time were using a phrase that, in their professional world, functions like a fire alarm. Rapid intensification, 2 words, and in the context of a tropical cyclone system, 2 of the most dangerous words in the English language. The storm's name is Sinlaku, and it is heading, with the kind of directional certainty that makes forecasters reach for their worst-case scenario language, toward United States soil. Now, I know what some of you are thinking. The United States is a big country. Typhoons happen in the Western Pacific. This sounds like the kind of geographic nuance that gets stretched into a headline. So let me be precise, because precision is exactly what this moment requires. The United States territory directly in the path of Super Typhoon Sinlaku is Guam, and the northern Mariana Islands. And if you have spent your life on the continental United States thinking of these places as abstract dots on a Pacific map, I want to invite you to reconsider that frame, because Guam is home to approximately 160,000 American citizens. The northern Mariana Islands hold another 50,000. These are people with American passports, American rights, American lives built on American soil. Soil that is right now in the projected path of a monster, and almost no one in the continental United States is paying attention. That is what this video is about. Not just the storm itself, though the storm is extraordinary in ways we are going to dig into deeply, but the full picture, the meteorology, the history, the infrastructure, the military dimensions. Because Guam is not just a residential island, it is the most strategically significant piece of American real estate in the Pacific. Home to military installations whose importance to U.S. defense posture in the Indo-Pacific cannot be overstated. The climate science that explains why storms like Sinlaku are becoming more powerful more quickly than they used to. And the warning systems, the preparation gaps, the lessons from the storms that came before. All of it. Because this storm deserves the full account. So let us start from the beginning. Chapter 1. What rapid intensification actually means. There is a difference between a storm that is dangerous and a storm that is dangerous in a way that forecasters specifically dread. The difference is predictability. A strong tropical cyclone that builds gradually over days gives forecasters time to refine their track models, gives emergency managers time to issue warnings, gives populations time to evacuate. The system is still potentially lethal. The destruction is still real. But the timeline allows for response. Rapid intensification removes that timeline. The official meteorological definition of rapid intensification is a sustained wind speed increase of at least 35 miles per hour, or 30 knots, within a 24-hour period. That is the formal threshold. In practice, the storms that earn the most alarmed attention from the scientific community are the ones that blow past that threshold the way Sinlaku did. Not 35 miles per hour in 24 hours, but something more like double that, in a window that compressed the storm's development from manageable to catastrophic in a span of time that barely allowed the warning infrastructure to keep up. To understand why rapid intensification is so specifically frightening, you need to understand how tropical cyclones work at a fundamental level. A tropical cyclone, whether you call it a hurricane in the Atlantic, a typhoon in the Western Pacific, or a cyclone in the Indian Ocean, these are all the same phenomenon wearing different regional names, is at its core a heat engine. It extracts thermal energy from warm ocean water, converts that energy into the mechanical work of wind and circulation, and sustains itself as long as the ocean beneath it remains warm enough and the atmospheric conditions above it remain favorable. The engine has specific requirements. It needs sea surface temperatures above approximately 26 degrees Celsius to sustain itself, though the most powerful systems tend to develop over water that is significantly warmer than that threshold. Water in the 29, 30, even 31 degrees Celsius range, which in the Western Pacific in the current era of ocean warming is increasingly common. It needs low wind shear, the change in wind speed and direction with altitude. High wind shear tears apart the organized convective structure of the storm, disrupting the warm core and preventing the intensification cycle from operating efficiently. And it needs a deep layer of warm water. Not just a warm surface, but warmth extending downward through the water column, so that as the storm's circulation churns and mixes the ocean beneath it, it is not pulling up cold water from below that would act as a natural brake on intensification. When all three conditions are simultaneously optimal, warm, deep ocean heat content, low wind shear, moist and unstable atmosphere, the result is what meteorologists call a high potential intensification environment. A racetrack with no speed bumps. The Western Pacific Ocean in the current climate era is providing that racetrack with terrifying frequency. But let us be specific about Sinlaku, because the way this storm developed is not just remarkable in the context of this year or this season. It is remarkable in the context of recorded meteorological history. Sinlaku formed from a tropical disturbance in the Western Pacific in the way that many typhoons begin. A cluster of thunderstorms, an area of organized convection, a nascent circulation that the Joint Typhoon Warning Center and the Japan Meteorological Agency were watching with interest but not yet alarm. It was a system, a potential system, something to monitor. And then, within a window of approximately 36 hours, it became something else entirely. The sea surface temperatures in the path of the developing system were running between 30 and 31 degrees Celsius, at the high end of what the Western Pacific typically produces in typhoon season, and significantly elevated compared to historical averages for this region and time of year. The ocean heat content, the measure of warm water depth that determines how much thermal energy is available to the storm, was among the highest values ever recorded for this part of the Pacific. The atmospheric wind shear over the system's development area dropped to near zero at the critical moment of organization. And the atmosphere above the system was loaded with water vapor, providing the moisture that feeds the thunderstorm towers that form the eye wall of a typhoon and drive the intensification cycle. The conditions were not just favorable, they were historically anomalous in their combination and intensity. And Sinlaku responded the way a fire responds to a blast of pure oxygen. In 36 hours, the system went from a tropical storm with maximum sustained winds of approximately 65 miles per hour, a system that, in that form, would cause significant damage but would not be making international headlines, to a super typhoon with maximum sustained winds exceeding 180 miles per hour and gusts that meteorologists were estimating above 215 miles per hour in some sectors of the eye wall. For context, the Saffir-Simpson hurricane wind scale tops out at Category 5, defined as sustained winds above 157 miles per hour. Sinlaku did not merely cross that threshold, it crossed it and kept going. At its peak intensity, the Joint Typhoon Warning Center was recording a minimum central pressure, the measure of how deep the storm's low-pressure core has dropped, the single most reliable indicator of a typhoon's raw power, that placed Sinlaku among the most intense tropical cyclones recorded in the Western Pacific Basin in the satellite era. That is not a casual characterization. The Western Pacific produces the most intense tropical cyclones on the planet. It is the basin where the records are set. It is where Typhoon Tip formed in 1979 with a central pressure of 870 hectopascals, still the lowest recorded central pressure of any tropical cyclone in history. The Western Pacific is where Typhoon Haiyan made landfall in 2013 with wind speeds so extreme that some measurement instruments at the point of landfall simply stopped working, unable to record values beyond their design specifications. When you say a storm is among the most intense in the Western Pacific Basin in the satellite era, you are placing it in extraordinary historical company. Sinlaku earned that company, and it earned it while pointing at Guam. Chapter 2: The Island in the Crosshairs. Most Americans, if asked to place Guam on a map, would struggle. This is not a criticism. It is a geographic reality of a country that spans a continent and tends to orient itself accordingly. The Pacific Islands, Guam, the Northern Mariana Islands, American Samoa, the Marshall Islands, Palau, occupy a cognitive periphery in the continental American imagination that their legal and strategic significance does not warrant. So let us do the geography properly, because context matters enormously here. Guam sits in the Western Pacific Ocean at approximately 13 degrees north latitude, 144 degrees east longitude. It is the southernmost and largest island in the Mariana Islands chain, a volcanic archipelago that stretches roughly 800 kilometers north to south and includes the Northern Mariana Islands, which are a separate U.S. territory. Guam itself is an island of about 540 square kilometers, roughly the size of Chicago. Its highest point is Mount Lamlam at 407 meters above sea level. It is surrounded on all sides by the deepest ocean on Earth. The Mariana Trench, the deepest known point in the ocean, sits roughly 340 kilometers to the southwest of the island. in terms of position relative to the continental United States, Guam is approximately 9,700 kilometers west of California. It is closer to Japan than it is to Hawaii. It is in a time zone that is 17 hours ahead of the U.S. East Coast. It is by every metric of distance and geography at the far edge of the Pacific, and it is unambiguously American territory. Guam has been a U.S. territory since 1898, acquired following the Spanish-American War. Its residents are American citizens by birth. It is governed under U.S. federal law. Its residents pay U.S. federal taxes, though notably, they cannot vote in presidential elections, a constitutional anomaly that sits uncomfortably alongside their full citizenship status. They serve in the U.S. military at some of the highest per capita rates of any geographic community in the country. Guam is America. It is just America in a place that America's continental residents rarely think about. And the northern Mariana Islands, Saipan, Tinian, Rota, and the smaller islands of the chain are in the same category. A commonwealth in political union with the United States. Their residents are citizens. Their territory is U.S. territory, and their location in the path of Sinlaku makes them part of the same threat calculus. Combined, approximately 210,000 American citizens live on these islands. Now let us talk about what a Category 5 typhoon actually does to an island this size. The physics are not complicated, but they are worth walking through carefully because the language of storm categories, Category 1, 2, 3, 4, 5, has a tendency to become abstract, to function as a numerical ranking that conveys severity without conveying mechanism. Category 5 is not just very bad. Category 5 is a specific collection of physical processes that operate simultaneously on every structure, every tree, every person, every piece of infrastructure in the storm's path. And understanding those processes is essential to understanding why people who study these events for a living treat a system like Sinlaku with something that looks, if you watch them carefully, like fear. Start with the wind. 180 miles per hour of sustained wind, with gusts exceeding 200 miles per hour. These are not speeds that have intuitive meaning for most people because nothing in ordinary life produces them. A hurricane-force wind at these speeds does not behave like the wind you experience in a severe thunderstorm or a powerful winter storm. It behaves like a physical force that occupies and transforms the environment. Trees that have survived decades of tropical weather, trees with root systems evolved for exactly this purpose, trees that bend and flex and lean under normal storm conditions, are simply removed. Not bent over, not stripped of leaves, removed from the ground, roots and all, and deposited somewhere else. Wooden structures, unreinforced concrete structures, structures that were built to withstand the storms that were typical of this region 20 or 30 years ago, are systematically disassembled by the wind, piece by piece, until what remains is either a ruin or a foundation. The wind also operates at altitude. The roof of a building, any building, constructed by any method, acts as an airfoil under sustained Category 5 winds. The air moving over the top of the roof is moving faster than the air beneath it, creating a pressure differential that acts as an upward lift force on the entire roof structure. When that lift force exceeds the structural connection between the roof and the walls, the roof goes. It does not crack. It does not gradually fail. It is lifted as a unit, and then it is somewhere else. What remains is an open structure in which the walls, no longer braced by the roof structure they were connected to, begin to fail outward under the lateral wind loading. This is not a worst-case scenario. This is the expected outcome for structures not specifically engineered to Category 5 wind loading, which describes the majority of the built environment in any tropical island community, and wind is only the beginning. The storm surge is, in many historical typhoon events, the primary cause of casualties. Storm surge is the dome of ocean water that a tropical cyclone pushes ahead of itself as it moves. The product of the storm's low central pressure drawing the ocean surface upward, and the storm's circular wind field piling water toward the coast in the direction of motion. For a system of Sinlaku's intensity and scale, the predicted storm surge values on the coastlines directly in the path of the eye wall are not measured in feet. They are measured in stories. For a typhoon of Sinlaku's intensity making direct landfall on Guam, surge models were producing estimates of between 20 and 30 feet above normal sea level along the storm's most exposed coastal sectors. 20 to 30 feet. On an island that has extensive infrastructure within a few meters of sea level. On an island where the downtown waterfront district of Hagåtña, the capital, sits at elevations that a 30-foot surge would overtop completely. 20 to 30 feet of ocean water moving inland at the speed of a running human being, carrying with it every piece of debris that the wind has already turned into projectiles, is not a flooding event. It is a physical transformation of the coastal landscape. It removes what was there and deposits ocean in its place. And then there is the rainfall. Tropical cyclones at this intensity produce rainfall rates that are essentially incomprehensible in terms of human experience with rain. Sinlaku's rain bands, in the hours before the eye wall passage, were producing localized rainfall rates of 2 to 4 inches per hour. The eye wall passage itself, the period of most intense rain, coinciding with the most intense wind, was producing rainfall that meteorological instruments describe as torrential, but that witnesses describe with words like, "You could not breathe in it. You could not distinguish rain from air." The water was not falling so much as it was occupying the atmosphere at every level simultaneously. Guam's terrain, volcanic, with steep ridgelines and deeply incised river valleys, channels that rainfall into flash flood events that operate independently of the coastal surge. While the coastlines are being inundated from the sea, the interior hillsides and valleys are experiencing flash floods, carrying meters of water and debris through channels that were roads and footpaths minutes before. Infrastructure in the valley floors, bridges, drainage culverts, utility conduits, is simply gone. This is the physical reality that 210,000 American citizens were facing as Sinlaku approached. And it is the physical reality that the rest of America was, by and large, not watching. Chapter 3. The military dimension. Nobody is mentioning. There is a conversation about Guam that almost never appears in the mainstream coverage of typhoons threatening the island. It does not appear because it involves dimensions of American strategic interest that are awkward to discuss alongside humanitarian concern, because mixing those two registers, the lives of civilians and the protection of military assets. Feels uncomfortable in the context of a disaster. But it is an essential part of understanding why this storm matters to the United States in ways that extend far beyond the tragedy of its human cost. Guam is not simply a residential island with American territorial status. It is, in the plain assessment of the U.S. Department of Defense and the broader Indo-Pacific Command, the single most strategically significant piece of real estate the United States controls in the Pacific. Let me be specific about what that means. Andersen Air Force Base occupies the northern plateau of Guam and is one of the largest Air Force installations in the Pacific. It is a primary forward operating base for U.S. long-range bomber aircraft, the B-52s, the B-1s, the B-2s that form the backbone of America's conventional and nuclear-capable air power in the region. Its runways, fuel storage, maintenance facilities, munitions storage, and support infrastructure represent an investment of many billions of dollars and decades of development. More importantly, its geographic position, roughly 2,500 kilometers from the Taiwan Strait, roughly 3,000 kilometers from the Korean Peninsula, well within operational range of virtually every potential flashpoint in the Indo-Pacific, makes it irreplaceable in the current security architecture. Naval Base Guam is the home port for submarines of the Pacific Fleet. In any conflict scenario involving the South China Sea, the Taiwan Strait, or the broader Indo-Pacific, those submarines are among the first and most critical assets that would be deployed. The base's position at the western edge of U.S. territorial waters in the Pacific gives those submarines their operational reach. Joint Region Marianas coordinates all U.S. military activity across Guam and the Northern Mariana Islands and serves as a command and logistics hub for the entire Indo-Pacific region. The strategic significance of this infrastructure has grown, not diminished, in recent years as the U.S. military has been accelerating its force posture in the Indo-Pacific in response to China's expanding military capability and increasingly assertive regional posture. The military construction program on Guam over the past decade has been one of the largest in the history of U.S. military basing. Billions of dollars invested in new facilities, hardened infrastructure, expanded runway capacity, underground fuel storage, and the construction of new Marine Corps Base Camp Blas, the first new Marine base to be built since 1952. All of that infrastructure is on a small island, an island that is, at this moment, in the direct path of one of the most powerful tropical cyclones ever recorded in the Western Pacific. The military dimensions of this vulnerability are not hypothetical. In 2023, a report by the U.S. Government Accountability Office specifically examined the climate resilience of U.S. military installations in the Pacific and found that typhoon risk, specifically the increasing frequency and intensity of extreme typhoon events, was among the most serious physical threats to the continued operational capacity of bases in Guam and the Marianas. The report noted that existing facilities were designed to withstand wind speeds well below what systems like Sinlaku are now capable of producing. That hardening to higher design standards was underway but incomplete. In plain English, some of the most strategically important military facilities the United States operates in the world are not fully hardened against the intensity of typhoon that is now bearing down on them. And this is not a new problem that nobody saw coming. It is a documented vulnerability that has been known, reported, and funded for improvement on a timeline that the accelerating intensity of Western Pacific typhoons is threatening to outpace. The relationship between military preparedness and extreme weather in the Pacific is something that the defense community has been wrestling with in its internal documents for years, while the broader public conversation about Guam focuses, when it focuses at all, on the tourism economy and the proximity to Japan. The strategic reality is more stark. Guam is a forward operating base for American power projection in the most geopolitically sensitive region on Earth, and it is regularly in the path of the most powerful storms on Earth. And the combination of those two facts creates a vulnerability that is simultaneously a military problem, a climate adaptation problem, and a humanitarian problem, and that rarely gets the coherent, integrated public attention it deserves. Super Typhoon Sinlaku is not just a natural disaster threatening American citizens. It is a stress test of American strategic infrastructure at a moment of significant geopolitical tension. It is a reminder that the geography that makes Guam so valuable militarily, its position at the edge of the Pacific, in the warm waters where the most powerful typhoons develop and track, is also the geography that makes it so vulnerable to exactly the kind of event that is happening right now. Both things are true simultaneously, and neither one makes the other less important. Chapter 4: Why this storm got so strong so fast. Let us talk about the science, not the surface-level science that fills 3-minute television weather segments, but the actual mechanisms, the oceanographic and atmospheric processes that allowed Sinlaku to go from a tropical storm to one of the most powerful typhoons in recorded history in a window of time that left emergency managers scrambling. Because understanding why this happened is not just academically interesting, it is directly relevant to what is happening to our planet and what storms like this are going to look like in the decades ahead. Start with the ocean. The Western Pacific Ocean is warmer than it has ever been in the instrumental record. Not warmer in the abstract, not warmer in the kind of subtle way that requires statistical analysis to detect. Warmer in ways that are measurable in real time by the network of Argo floats, moored buoys, and satellite sensors that now provide nearly continuous coverage of ocean surface and subsurface temperature across the globe. The sea surface temperature anomaly in the region where Sinlaku developed, the difference between current temperatures and the historical average for this region and time of year, was running between 1.5 and 2 degrees Celsius above the long-term mean. In the language of climate science, that is an enormous anomaly. It represents an enormous amount of additional thermal energy stored in the water column. Ocean heat content, the integrated measure of thermal energy stored in the water column to a depth of several hundred meters, was at record or near record levels in the Western Pacific this season. This matters specifically in the context of rapid intensification because of a phenomenon called the cold wake effect. As a tropical cyclone moves over the ocean, its winds generate wave action and upwelling that mix cooler water from below the surface layer upward, replacing warm surface water with cooler subsurface water. This acts as a natural brake on intensification. The storm is literally cooling the water it needs to sustain itself. In historical conditions, this mixing effect was one of the primary factors that limited how fast and how far tropical cyclones could intensify. But when the warm water layer is deep, when the ocean heat content extends hundreds of meters below the surface, rather than just the top few tens of meters, the mixing brings up water that is still warm rather than cold. The break does not engage, or it engages only partially at greatly reduced effect. In the development region of Sinlaku, the warm water layer was exceptionally deep. The mixing driven by the storm's circulation was pulling up water that was still warm enough to fuel continued intensification rather than damping it. The cold wake effect, which historically would have slowed or capped the storm's development, was essentially absent. The atmosphere cooperated as well in every dimension that matters for typhoon intensification. Wind shear, the variation in wind speed and direction, with altitude that tears apart the organized structure of tropical cyclones, was near zero over the development region during the critical intensification phase. This is not typical. Significant wind shear is the atmospheric immune system's primary defense against runaway tropical cyclone intensification. When it drops to near zero, the storm's organization can proceed unimpeded, and the warm core structure that drives intensification can build with maximum efficiency. The reason wind shear was so low during Sinlaku's intensification window is itself connected to the broader atmospheric circulation pattern over the Western Pacific, a pattern that has been described by climate scientists as increasingly influenced by the warming ocean temperatures that are raising sea surface temperatures and sea level simultaneously. The atmospheric dynamics of a warmer ocean are different from those of a cooler one, and those differences, in some configurations, produce the kind of extended low shear windows that give systems like Sinlaku the opportunity to exploit the warm ocean beneath them without interference. There is one more atmospheric ingredient that deserves specific attention: water vapor. The atmosphere above the Western Pacific right now holds more water vapor than historical averages. This is a direct consequence of warmer ocean temperatures. Warmer water evaporates faster, loading the lower atmosphere with moisture. Water vapor is not just a passive component of the atmospheric environment, it is fuel. When water vapor condenses into the cloud droplets and rain that make up the thunderstorm towers of a typhoon eye wall, it releases latent heat, the energy that was stored when the water evaporated from the ocean surface. That latent heat release is what warms the storm's core, reduces its central pressure, and drives the intensification cycle. More water vapor in the atmosphere means more latent heat available to feed the storm's engine. The combination of these factors, anomalously warm, deep ocean heat content, near zero wind shear, elevated atmospheric moisture, created what climate scientists and meteorologists describe as a highly favorable environment for rapid intensification. Favorable is, of course, a word that requires reframing in this context. Favorable for the storm, catastrophic for everything in its path. Sinlaku responded to this environment with a symmetry and a violence that satellite imagery made visible in real time. The storm's eye, the clear, calm center around which the entire system rotates, contracted and sharpened as intensification proceeded. A process called eye wall replacement cycle that is characteristic of the most powerful tropical cyclones. The eye wall, the ring of most intense thunderstorm activity that surrounds the eye and is responsible for the highest wind speeds, tightened and organized into a near-perfect circular structure. Infrared satellite images of Sinlaku at peak intensity showed a system so geometrically organized, so structurally coherent, that meteorologists describing it in their professional communications used the word impressive, a word that, in the context of a system this destructive, carries its own kind of horror. The rapid intensification of Sinlaku is not a random event. It is not bad luck. It is the output of a specific, measurable, scientifically understood set of conditions that have been created, to a significant degree, by the changes that human industrial activity has made to the Earth's climate system over the past century and a half. The ocean is warmer because of those changes. The atmosphere holds more moisture because of those changes. The frequency with which the atmospheric conditions align to produce low shear, high moisture, high ocean heat content environments over the Western Pacific is changing because of those changes. This does not mean that Sinlaku would not have existed without climate change. Tropical cyclones have always formed in the Western Pacific. They always will. The Mariana Islands have been in the path of powerful typhoons throughout recorded history and long before it. What it means is that the ceiling of what these storms can achieve, the peak intensity that the physical environment allows them to reach, has been raised. The fuel supply has been increased. The atmospheric brakes have been weakened. And the result is that the storms that form in these conditions can get stronger, faster, and can sustain that strength over longer distances than the historical record would lead us to expect. Sinlaku is not just a typhoon. It is an illustration of what the changed atmosphere and ocean are now capable of producing. And it is heading toward American territory at 180 miles per hour. Chapter 5. The history of what happens when these storms arrive. Guam has been hit by typhoons before, many times. The island sits in what is informally but accurately called Typhoon Alley, the section of the Western Pacific where the warm waters, the latitude, and the prevailing atmospheric circulation patterns combine to funnel typhoons with some of the highest frequency of any comparable area on Earth. The residents of Guam and the northern Mariana Islands live with typhoon risk the way residents of Tornado Alley live with tornado risk. It is the background condition of life in that place. It shapes the architecture, the emergency preparedness culture, the seasonal rhythms of stocking supplies and monitoring forecasts. But knowing that typhoons come does not make the strong ones survivable without preparation. And the history of the island's most powerful strikes is a history of destruction so complete, so systematic, that it reads less like disaster narrative and more like the systematic erasure of a built environment and its replacement with ruins. The most instructive and most frequently cited historical reference point in discussions of Guam and extreme typhoon impacts is Typhoon Karen, which struck the island in November 1962. Karen was, by the standards of its era, a powerful typhoon. Maximum sustained winds estimated at approximately 175 miles per hour at landfall. The storm made a direct hit on the island, and the damage was comprehensive. Over 1,000 homes were destroyed. The agricultural industry was essentially eliminated. Power, water, and communication infrastructure failed island-wide. The recovery required years, and the storm prompted a wholesale reconstruction of building codes and infrastructure standards on Guam that shaped the built environment for decades afterward. But Karen is history, and the buildings built to post-Karen codes, stronger than anything that existed before 1962, designed for sustained winds of up to about 170 miles per hour, are now facing a storm that is producing winds above that design threshold. More recent and more directly relevant to the current situation is Typhoon Pongsona in 2002. Pongsona made landfall on Guam as a Category 4 storm with maximum sustained winds of approximately 144 miles per hour. The damage was severe. Hundreds of millions of dollars in infrastructure damage, power outages lasting weeks for much of the island, water system damage that required months of repair, and damage to military facilities at Andersen Air Force Base that temporarily reduced operational capacity. And Pongsona was a Category 4. Sinlaku is Category 5, with sustained winds running substantially above Category 4 levels. The relationship between wind speed and destructive power is not linear. It follows roughly a cubic relationship, which means that the destructive power of wind is proportional to the cube of its speed. Going from 144 miles per hour to 180 miles per hour is an increase in speed of about 25%. The increase in destructive wind force associated with that speed difference is closer to 95%. Almost double the destructive energy, not 25% more damage. Nearly double. The most directly analogous recent event in terms of intensity, though not in terms of U.S. territorial impact, is Typhoon Haiyan, which struck the Philippines in November 2013. Haiyan made landfall at or near Category 5. Intensity. Maximum sustained winds estimated at between 195 and 215 miles per hour, making it one of the strongest tropical cyclones at landfall in recorded history. The result was a catastrophe of a scale that reorganized how the international disaster response community thinks about tropical cyclone casualties. Over 6,000 people died. The city of Tacloban, with a population of roughly 200,000, was effectively destroyed. Storm surge in some coastal areas reached heights exceeding 7 meters above normal sea level, inundating entire neighborhoods that had never flooded in living memory. The lesson that emergency managers took from Haiyan was not just about the wind, it was about the surge. The catastrophic majority of casualties in Haiyan, the people who died in the thousands when the ocean rose 7 meters in the space of an hour, were people who had survived the wind but had not evacuated from the coastal surge zone, who had stayed in structures that were damaged by the wind but still standing, only to be overcome by water, who did not believe, based on their experience of previous storms, that the ocean could rise that high, that fast. The surge from Sinlaku on Guam's western coast, the coast most directly exposed to the storm's approach path, was being modeled in the worst-case scenario projections at heights comparable to what Haiyan produced in the Philippines. Not as a certainty, not as the most likely outcome, but as a physically plausible scenario given Sinlaku's intensity, forward speed, and approach angle. There is also the precedent of Typhoon Pamela, which struck Guam in 1976 and produced catastrophic damage across the island's central and northern sectors, and Super Typhoon Paka in 1997, which made direct landfall on Guam with maximum sustained winds at the time of passage estimated at approximately 170 miles per hour, setting a wind speed record for a landfalling typhoon on Guam that stood for decades. Paka caused approximately $500 million in damage in 1997 dollars. Power was out on parts of the island for weeks. The military bases sustained significant infrastructure damage. Each of these storms left its mark on the island in physical and institutional ways. Each one prompted new building codes, new emergency protocols, new investment in critical infrastructure hardening. Each one was, when it occurred, described as an extreme event, a rare combination of intensity, track, and timing that produced exceptional destruction, and each one was less powerful than Sinlaku. That is the historical context within which emergency managers and military commanders on Guam were operating as Super Typhoon Sinlaku closed on the island. Not ignorance of what powerful typhoons can do. These are people with institutional memory and professional training built on exactly those events. But awareness, very clear and very specific awareness, that the storm bearing down on them was operating outside the range of what their island's history had directly prepared them for. That the design standards, the evacuation plans, the surge projections, the infrastructure hardening, all of it was calibrated to historical experience. And historical experience had just been exceeded by a storm that the climate system, running hotter and wetter and more energized than in any previous period of the instrumental record, had produced with a speed and an intensity that left remarkably little time to prepare. Chapter 6. The warning system and its limits. One of the things that separates a typhoon catastrophe from a typhoon event is warning time. Specifically, the combination of how early a warning is issued, how accurate that warning is, and how effectively it is communicated to and acted upon by the population in the storm's path. The United States operates what is arguably the most sophisticated tropical cyclone forecasting infrastructure in the world. The National Hurricane Center in Miami monitors Atlantic and Eastern Pacific systems. The Joint Typhoon Warning Center, a combined U.S. Navy and Air Force unit located in Pearl Harbor, Hawaii, is responsible for Western Pacific and Indian Ocean tropical cyclone forecasting, making it the primary official source of Sinlaku track and intensity guidance. The National Weather Service's Weather Forecast Office in Tian, Guam, provides the island-specific watches, warnings, and impact forecasts that translate the JTWC's basin-wide guidance into actionable local information. The forecasting technology available to these agencies in 2024 and 2025 is transformatively better than what existed even a decade ago. Satellite imagery, with much higher resolution and more frequent update cycles than previous generations. Improved reconnaissance aircraft data from NOAA and Air Force Reserve, Hurricane Hunter missions that fly directly into the storm to measure conditions that satellites cannot see. Numerical weather prediction models, the complex computational systems that simulate the atmosphere and ocean to generate track and intensity forecasts that are updated with increasingly high-resolution data and run at increasing computational resolution. Ensemble forecasting systems that run dozens of slightly different model variants simultaneously to characterize the range of possible storm evolution scenarios. All of this technology was applied to Sinlaku. The track forecast, the prediction of where the storm's center would go, was commendably accurate. The Joint Typhoon Warning Center's 5-day track forecast, issued when Sinlaku was still a tropical storm, had the storm's projected landfall zone over Guam within a margin that, for a 5-day tropical cyclone forecast, represents good forecasting performance. The island's emergency managers had days of advance notice that a major storm was coming and that Guam was in its likely path. The intensity forecast was the harder problem. Rapid intensification remains one of the most challenging forecasting problems in meteorology. The physical processes that drive it operate at spatial and temporal scales that current numerical weather prediction models do not capture with full accuracy. The ocean-atmosphere interactions that determine whether and how quickly a storm intensifies depend on fine-scale details of ocean temperature structure, atmospheric humidity profiles, and circulation patterns that even the best current models represent only approximately. And in the case of Sinlaku, the storm intensified faster than the high-end forecast scenarios suggested. This is not a criticism of the forecasters. It is a statement about the current state of the science. Rapid intensification forecasting has improved significantly over the past decade. The models are better, the data inputs are better. The forecasters are better at recognizing the signatures of potential rapid intensification events. But the improvements have not yet reached the point where the full magnitude of an exceptional rapid intensification event can be reliably predicted 48 or 72 hours in advance. When Sinlaku went from tropical storm to Category 5 Super Typhoon in 36 hours, it performed at the extreme upper end of the distribution of possible outcomes. Not outside what the models suggested was physically possible, but beyond what the probabilistic guidance indicated was likely. The practical consequence of this for Guam was a warning timeline that was compressed compared to what a more gradual intensification would have provided. Guam's emergency management agency, the Guam Homeland Security and Office of Civil Defense, issued a series of escalating warnings as Sinlaku approached. Typhoon watch, then typhoon warning, then the conditions of readiness declarations that trigger specific protective actions at military installations and activate government emergency operations. The sequence of warnings was appropriate and professional. The challenge was not the warning system's operation. The challenge was the human response to it. And this is where the typhoon history of the island becomes relevant in a deeply practical way. Populations that live in high typhoon frequency environments develop a complex relationship with storm warnings. They have experienced many warnings that did not result in the predicted level of impact. Storms that weakened before arrival, storms that tracked away at the last minute, storms that produced significant damage but were manageable. This experience, accumulated over years and decades, creates a psychological calibration that is not irrational, but that can be dangerous when the actual storm exceeds historical experience. It is called hurricane fatigue, or typhoon fatigue in this context. The exhaustion of repeated mobilizations for storms that, in the end, did not require the full level of response that the warnings implied, and it produces a tendency in some portion of the population, the portion with the most direct experience of previous near misses, to discount the high-end impact scenarios in favor of the more moderate outcomes that their personal experience has made more familiar. For Sinlaku, the high-end impact scenarios were not being offered as worst cases to be dismissed. They were being driven by a storm that was, objectively, at the upper limit of what the Western Pacific produces. But the translation of that objective reality into individual behavioral decisions, whether to evacuate the coastal surge zones, whether to shelter in place in a reinforced structure, or to take refuge with relatives in a sturdier building further from the coast, was playing out against a background of typhoon-experienced island residents whose calibration for storm severity was based on historical events that Sinlaku had already exceeded in intensity. This is one of the most difficult problems in disaster preparedness, not the technology, not the science, the human communication problem of convincing people, on the basis of forecast models and historical analogies, to take actions commensurate with a risk that exceeds their personal experience. The people who stayed in coastal surge zones for Haiyan's surge in 2013 were not, for the most part, foolish or reckless. They were operating on the basis of a reasonable prior belief, built from experience, about what storm surge could do. That belief was wrong for that storm. And for those people, it was fatally wrong. The warning system for Sinlaku was as good as the current state of meteorological science and emergency management practice could make it. That is genuinely good. The forecasters, the emergency managers, the military commanders, the local government officials who worked the days and hours before the storm's arrival, they did their jobs with professionalism and urgency. But the warning system operates in a world where the storms are getting more extreme faster than the public's intuition about extreme storms is updating. Where the gap between the historically typical and the physically possible is growing, and where the consequence of that gap, the people who stayed because they had stayed before and it had been okay, facing a storm that was nothing like the ones they had stayed for before, is measured not in meteorological statistics, but in human lives. There is one more dimension of the warning system's limits that deserves attention, and it concerns not the island residents, but the broader American public watching from the continent. The continental United States has a robust, well-developed, culturally embedded awareness of hurricane risk. The Atlantic hurricane season, from June through November, is tracked obsessively by media, weather services, and a large and engaged public that has been educated by decades of storms: Hugo, Andrew, Katrina, Sandy, Harvey, Irma, Maria, Ida, into understanding what tropical cyclone threats look like and why they matter. The naming conventions are familiar. The track forecast cone graphic is almost universally recognizable. The press conferences from the National Hurricane Center have cultural familiarity. When a hurricane threatens Florida or Louisiana or the Carolinas, the national media apparatus activates at a scale commensurate with the threat. When a typhoon threatens Guam, none of that apparatus activates in the same way. The Joint Typhoon Warning Center, which does for the Western Pacific what the National Hurricane Center does for the Atlantic, does not have the same cultural visibility. The track forecast graphics it produces are not broadcast on national television with the same urgency. The names, Asian names, following the naming conventions of the Pacific Basin, do not carry the same immediate resonance for an American continental audience as Atlantic hurricane names do. The islands themselves, Guam, Saipan, Tinian, do not trigger the same national protective instinct as Miami, New Orleans, or New York. This is a failure of collective civic awareness about the geography of American territory and the reality of American citizenship across the Pacific. It is a failure that has real consequences in terms of federal political attention, congressional appropriations, urgency, national solidarity with affected communities. Every time a major typhoon strikes United States territory in the Western Pacific, and the continent mostly looks the other way. 160,000 American citizens on Guam, 50,000 on the northern Mariana Islands, facing a monster, and almost no one on the continent watching. Chapter 7. The Infrastructure Reckoning. When the wind stops and the surge recedes and the sky clears the way it always does after a typhoon. That particular Pacific blue, washed and luminous, that seems almost offensive in its beauty against the devastation beneath it. What gets left behind is not just debris and ruin. What gets left behind is a ledger of every decision made or deferred over the preceding years and decades about what to build, how to build it, what to harden, what to leave unhardened, where to invest, and where to defer investment in the name of budget constraints or competing priorities. The storm does not destroy randomly. It destroys selectively in proportion to the choices that were made about infrastructure before it arrived. And in the aftermath, those choices are exposed with a clarity that no audit, no Inspector General report, no GAO study can produce. The ledger that Sinlaku opened on Guam was, in some dimensions, better than the historical ledgers of previous storms. And in others, it was a stark account of deferred work meeting accelerated consequence. Start with the power grid. Guam's electrical infrastructure has been a subject of concern and controversy in U.S. territorial governance for years. The Guam Power Authority, which operates the island's generation and distribution system, has faced consistent criticism from residents, federal oversight bodies, and infrastructure analysts for operating a system that is aging, undersized for the island's energy needs, and insufficiently hardened against the typhoon conditions that the island faces regularly. The generation capacity is dominated by older fossil fuel plants, heavy fuel oil and diesel generators that were not designed to the wind load standards that modern engineering practice would specify for a Category 5 typhoon environment. The distribution network, the poles, lines, transformers, and switching equipment that carry electricity from generation to consumers, uses above-ground infrastructure in significant portions of the island's layout. Infrastructure that is among the most vulnerable components of any utility system to high wind events. The experience of previous typhoons on Guam has repeatedly demonstrated what happens when above-ground power distribution meets Category 4 and 5 winds. It fails completely, island-wide, and for extended periods. After Typhoon Paka in 1997, large portions of Guam were without power for weeks. After Typhoon Pongsona in 2002, the timeline for full power restoration stretched to months. The pattern is well established, well documented, and has been the subject of repeated recommendations for infrastructure hardening, specifically for the undergrounding of critical distribution lines in areas most exposed to typhoon wind loading. The progress on that hardening has been real but slow. Some undergrounding has been completed. Some generation capacity has been modernized. But the pace of improvement, measured against the intensity trajectory of Western Pacific typhoons in the current climate era, has not been sufficient to close the vulnerability gap. Sinlaku arrived at Guam's electrical infrastructure at a point in the hardening program where the work that had been done was meaningful, but the work that had not yet been done was also meaningful. The consequence: an island-wide power outage of the kind that previous storms had produced, but potentially more severe in extent and longer in duration, because the maximum wind loading that the grid experienced under Sinlaku exceeded the design assumptions of even the portions of the system that had been upgraded. Power outage on Guam is not merely an inconvenience, it is a cascading systems failure. The water system, Guam's drinking water distribution depends on electrically operated pumping stations, fails within hours of power loss, or shifts to backup generator operation that is limited by fuel availability and generator maintenance state. Medical facilities shift to emergency generator power, which limits their operational capacity and creates a fuel management challenge that becomes critical within days if normal fuel supply chains have been disrupted. Communication systems, cellular towers, internet infrastructure, emergency notification systems operate on backup power with finite runtime. Refrigeration for food and medicine fails. The social support systems that a functioning modern community depends on, banking, fuel distribution, supply chain logistics, are suspended. And all of this is happening in the immediate aftermath of a storm that has simultaneously damaged or destroyed a significant fraction of the housing stock, injured an unknown number of residents, blocked road networks with debris that prevents emergency vehicle access, and potentially contaminated water sources with the same surge water that inundated coastal areas. The cascade is not hypothetical. It has been documented in exhaustive and heartbreaking detail in every major typhoon post-event assessment for Guam. It is known. The dependencies are mapped. The failure modes are understood. The question that every infrastructure assessment comes back to is the same question. In the time between storms, when the urgency is not visible and the budget pressures are constant, and the political attention of the continental federal government is oriented toward other priorities, does the work get done? The water infrastructure deserves its own specific attention because water is not a convenience. It is a survival requirement with a timeline measured in days. Guam's water system draws from a combination of surface water sources in the southern part of the island and the northern Guam Lens Aquifer, a freshwater aquifer that underlies the limestone terrain of the island's northern plateau. The aquifer is a critical resource. It supplies a significant fraction of Guam's drinking water, and it is vulnerable in ways that a typhoon directly exploits. Storm surge inundation of coastal areas adjacent to the aquifer recharge zone can introduce saltwater infiltration into the freshwater lens, a process called saltwater intrusion that can degrade water quality for months or years after a single extreme surge event. The aquifer does not flush quickly. Salt water that enters the freshwater lens during a surge event does not simply drain away when the surge recedes. It diffuses slowly through the porous limestone, contaminating the resource in ways that require time, infrastructure investment, and in some cases, years of careful management to remediate. For Guam, already dealing with chronic concerns about aquifer sustainability in the context of population growth and military construction, a major saltwater intrusion event from Sinlaku's surge represents not just a short-term water emergency, but a potential long-term water security challenge on an island that has limited alternatives. The road network failure is less dramatic in its immediate life or death implications, but is enormously consequential for the recovery. Guam's road network, primarily a single ring road around the island's perimeter with a limited network of cross-island routes, is the circulatory system of the recovery effort. Emergency responders move on it. Fuel. Trucks move on it. Medical supply chains move on it. The debris from a Category 5 typhoon, fallen trees, structural wreckage, utility poles, vehicle components, roofing material, every category of material that the wind has stripped from the built environment and deposited on every road surface simultaneously, closes it. The clearing operation, moving from most critical routes to secondary routes, is a process that takes days to weeks, depending on the volume of debris and the availability of heavy equipment, much of which is itself subject to damage or displacement in the storm. During the period when the roads are blocked and the power is out, and the water system is uncertain, and the communication networks are operating on backup power, the 210,000 residents of Guam and the northern Mariana Islands are in an environment that demands a level of self-sufficiency that modern urban and suburban populations are not, by and large, calibrated for. The recommendation from Guam's Emergency Management Agency for pre-storm preparations has consistently been a minimum of 72 hours of food, water, and essential supplies. Typhoon preparedness guides push that to 7 days for major events. The experience of previous storms, where full utility restoration has taken weeks or months, suggests that even 7 days is an underestimate for the recovery horizon of an event at Sinlaku's intensity. And then there is the hospital. Guam Memorial Hospital, the island's primary civilian medical facility, is a building that has been the subject of patient safety concerns and infrastructure criticism for years predating Sinlaku. A federal inspection process that oversees Medicare and Medicaid compliance has repeatedly flagged deficiencies at the facility. The physical plant, aging, in a location on the island that gives it some exposure to typhoon wind loading, is not the hardened, purpose-built Category 5 refuge structure that the island's primary medical facility in a typhoon frequency environment ideally should be. The military medical facilities at the bases represent an additional resource, but they are primarily oriented toward military patient care, and their capacity for civilian surge is limited. The convergence of mass casualty potential from a Category 5 typhoon strike with a civilian medical infrastructure that was already operating under strain before the storm is one of the most direct and concerning dimensions of the ledger that Sinlaku opened on Guam. It is also one of the dimensions that was most clearly visible in advance. Not a surprise, discovered in the aftermath, but a documented vulnerability that had been identified and flagged and inadequately addressed across multiple budget cycles and multiple administrations. The communication infrastructure deserves its own place in this accounting because it operates as both a practical lifeline and a psychological one. Cellular towers in Guam are mounted on structures that are rated to specific wind loads. And like much of the island's infrastructure, those ratings reflect design standards written for historical storm intensity ranges, not the range that Sinlaku represents. When towers fail, when the wind loading exceeds the structural capacity of the mount and the tower comes down, the cellular network it served goes dark. The geographic density of Guam's cellular infrastructure means that a single tower failure can black out communication for large residential areas simultaneously. Emergency communication falls back to the island's emergency broadcast system and to amateur radio networks, which are maintained by a dedicated community of licensed operators who function as a critical backup communication layer during major disasters. Valuable, essential even, but an emergency fallback, not a replacement for the full communication architecture that a community in a mass casualty event requires. The internet infrastructure, the physical undersea cable connections that link Guam to the global internet, represents another vulnerability that has received increasing attention in the defense and telecommunications communities in recent years. Guam sits at the junction of several major trans-Pacific undersea cable routes. These cables carry enormous fractions of the data traffic between Asia and the Americas. The cable landing stations on Guam, the physical facilities where undersea cables come ashore and connect to the terrestrial network, are exposed to the same typhoon conditions as every other piece of surface infrastructure on the island. Physical damage to cable landing infrastructure could affect not just Guam's own connectivity, but the broader trans-Pacific communications architecture that the cables support. The infrastructure reckoning that follows a storm like Sinlaku is not a moment of discovery. It is a moment of accountability. The vulnerabilities were known. The decisions about whether and how quickly to address them were made in the years and decades before the storm arrived. And the storm, with its perfect indifference to those decisions, simply reveals the ledger. Chapter 8. What the climate science actually tells us about the future. There is a tendency in the coverage of extreme weather events to present the science as a backdrop. A paragraph or two of context about climate change inserted between the dramatic footage and the human interest stories, performing the function of explanation without really inhabiting it. The science gets a sentence or two, and then the story moves on. That approach is inadequate for what the science actually says. Because what the climate science actually says about the future of tropical cyclones in the Western Pacific is specific, empirically grounded, and considerably more alarming than the brief contextual paragraph usually conveys. Let us actually inhabit the science. The fundamental relationship between ocean temperature and tropical cyclone intensity has been understood for decades. Warmer ocean, more thermal energy available to the storm, higher potential peak intensity. This is physics. It is not in scientific dispute. The disagreement in the scientific literature is not about whether warmer oceans fuel more intense tropical cyclones. They do. but about the specifics. How much more intense, at what rate, with what geographic distribution, and in combination with which other atmospheric changes. The body of work on tropical cyclone intensity trends in the Western Pacific has grown substantially over the past decade, driven by improving data quality, longer observational records with better satellite coverage, and increasingly sophisticated climate model simulations. The picture that emerges from this literature is not simple, but its most important features are clear. First, the proportion of tropical cyclones that reach Category 4 or 5 intensity, the most destructive end of the storm spectrum, has been increasing. The total number of tropical cyclones globally has not increased significantly. In some analyses, it may have decreased slightly, as warming has changed the atmospheric dynamics that favor cyclone genesis. But the fraction that reach major intensity has shifted upward. The storms that form are, on average, more likely to reach the top of the intensity scale than they were in the mid-20th century. Second, the rate of intensification is increasing. The phenomenon of rapid intensification, the 35 knot in 24 hours threshold, is occurring more frequently, and the most extreme intensification events, the ones where storms go from moderate tropical cyclone to Category 5 in a matter of hours, are becoming a larger fraction of the observed record. A study published in the peer-reviewed literature within the past several years found that the probability of rapid intensification events in the Western Pacific Basin has increased significantly over the satellite era, and that the most extreme intensification rates, the events at the upper tail of the distribution, the events like what Sinlaku produced, have increased disproportionately relative to the overall rapid intensification trend. This is not a linear, gradual trend. It is a trend concentrated at the extremes. The storms that were already rare are becoming less rare. The events that were historically exceptional are beginning to populate the record with a frequency that the word exceptional can no longer adequately describe. Third, the geographic range over which intense tropical cyclones can maintain their intensity is expanding poleward. As ocean warming extends the area of warm surface water beyond its historical boundaries, the zone within which tropical cyclones can sustain themselves, and the zone within which they can undergo rapid intensification, is moving toward higher latitudes. In the Western Pacific context, this means that the northward extent of the region capable of supporting intense typhoon activity is increasing, bringing storm tracks that were historically confined to lower latitudes closer to Japan, Korea, China's northern coast, and the latitude band that includes Guam and the Marianas. Fourth, and this is the one that is least discussed and perhaps most important for the specific question of Guam's future. Sea level rise is systematically increasing the destructive reach of storm surge. The surge itself is determined by the storm's intensity, size, and forward speed. The changes in those parameters described above are already producing higher surge potential. But surge's destructive reach into land, how far inland the surge water penetrates, how deep it gets over ground that was previously above flood level, is a function of the relationship between surge height and the elevation of the land it encounters. As sea level rises, the baseline from which surge is measured rises with it. A storm that produces a 20-foot surge from a sea surface that is 1 foot higher than the historical baseline produces an effective inundation height 1 foot higher than historical experience with the same surge would suggest. It is a compounding of threats that works systematically against every piece of coastal infrastructure and every coastal community. Guam's coasts, like every Pacific Island coast, have been experiencing the effects of sea level rise for decades. The regional sea level rise in the Western Pacific, which has been occurring faster than the global average due to changes in ocean circulation patterns associated with climate change, has raised the baseline against which every typhoon surge now operates. The storm that would have produced a specific inundation level 30 years ago produces a deeper, farther-reaching inundation today from the same surge height. Now put all of that together and ask, what does the future of typhoon risk look like for Guam? The answer, in the honest assessment of the climate science, is this. More frequent extreme intensification events, producing storms capable of Sinlaku level intensity with greater regularity than the historical record would suggest. A higher proportion of landfalling storms in the Category 4 to 5 range. More rapid intensification in the final hours before landfall, further compressing the warning to impact timeline. Higher storm surge impacts from the same storm intensity because of rising sea level. And all of this playing out against a background of infrastructure that was designed and built for the historical storm climate, not the future one. There is one more dimension of the climate science that the popular framing of typhoon intensity tends to miss, and it concerns what researchers call compound flooding, the interaction of storm surge with rainfall flooding and with the baseline sea level elevation. The most destructive flooding in tropical cyclone events is frequently not the result of any single flood mechanism operating in isolation. It is the result of multiple mechanisms operating simultaneously. The storm surge arrives from the sea. The rainfall-driven flooding arrives from inland waterways and drainage systems, overwhelmed by extreme precipitation rates. And both of these operate against a ground surface that, in the case of low-lying coastal terrain, may already be saturated from the storm's outer rain bands before the eye wall arrives. The compounding of these mechanisms produces flooding depths and spatial extents that are greater than the sum of their individual contributions would predict. A surge that would be manageable if the drainage systems were clear and the soil was unsaturated becomes catastrophic when those systems are already overwhelmed by rainfall and the soil is already at capacity. Climate change is not just intensifying the individual components, the surge height and the rainfall rate. It is increasing the probability that the extreme values of both components occur simultaneously within the same storm, producing compound flooding events whose aggregate destructive power represents a qualitatively different threat from what historical design standards were written to manage. For Guam, an island with a terrain of steeply incised river valleys on the southern end and low-lying limestone plateau on the north, with the aquifer recharge zone, the military facilities, and the major residential concentrations all on the relatively low-lying northern plateau. Compound flooding represents a specific and underappreciated threat dimension. The surge from the ocean coast and the drainage flooding from the rainfall combine in the low-lying terrain in ways that historical typhoon impact assessments have not fully modeled. The climate science does not say that Guam will be struck by a Sinlaku-level storm every year. It does not project a specific frequency or a specific future timeline. What it says is that the upper bound of what the physical system is capable of producing, the extreme that Sinlaku represents, is no longer as extreme relative to the distribution of possible events as it was in previous decades. The tail of the distribution has gotten fatter. The exceptional has gotten more probable. For emergency planners, for infrastructure engineers, for military base commanders, for the federal agencies responsible for the welfare of American citizens in the Pacific territories, what the climate science says translates into a design standard question. Are we building and hardening infrastructure for the historical climate, or for the climate we are actually living in? Are the building codes written for the storms of the past or the storms of the future? On Guam, the honest answer to that question has been somewhere in between, better than the standards of decades ago. Not yet fully calibrated to what the climate system is now demonstrably capable of producing. Getting there, but not there yet. And the pace of getting there has not matched the pace at which the climate system has moved the goalposts. Sinlaku did not create this problem. It illustrated it with the specificity and the authority that only a real storm at real intensity on a real island can provide. And the illustration will fade, as it always does, in the weeks and months after the cameras and the federal response teams leave, and the island begins its long, hard, undercovered recovery. The question that the science insists on asking, is what happens in the years between this storm and the next one. Whether the lesson is institutionalized in building codes and infrastructure investment and federal appropriations and military hardening programs, or whether it is filed and forgotten until the next Sinlaku writes it in the same indelible language. Chapter 9. The broader warning. Nobody is reading. There's a story underneath the story of Super Typhoon Sinlaku that is harder to tell because it does not have a single dramatic moment. It does not have a satellite image of a perfect vortex or a wind speed record or an eye wall making landfall. It is a slower story told in policy documents and budget line items and congressional hearing transcripts and the quiet, methodical work of people in federal agencies and military commands who have been raising the same concerns in different forms for years. It is the story of what the United States has and has not done to prepare its Pacific territories for the climate reality that Sinlaku represents. Let us start with the federal response architecture. When a hurricane strikes Florida or Louisiana, the federal disaster response ecosystem activates with a scale and a speed that reflects decades of hard-learned lessons and institutional investment. FEMA pre-positions supplies, coordinates with state emergency management agencies, stages federal resources, and has operational relationships with local emergency managers that have been built and tested across dozens of events. The National Guard, the Coast Guard, the Army Corps of Engineers, all of these institutions have well-developed protocols for responding to Atlantic Basin hurricane events in the continental United States and Puerto Rico. The Pacific territories operate within this system, but the geographic reality of their distance from the continental United States creates logistical constraints that do not apply in the same way to continental hurricane responses. Pre-positioning of supplies in Guam and the Marianas requires advance investment and advance logistical planning that is more difficult, more expensive, and more dependent on accurate long-lead forecasting than positioning supplies in a warehouse in Georgia for deployment to Florida after a hurricane. The response supply chains across the Pacific are longer. The transportation assets required, naval vessels, Air Force cargo aircraft, commercial shipping contracts, are more specialized and less immediately available than the truck fleets and State Guard aircraft that move supplies in continental responses. FAMA has a regional structure that includes the Pacific territories, and the agency has worked to improve its Pacific response posture in the years following major events in the region. The 2018 response to Typhoon Mangkhut, which caused significant damage in the Marianas, provided operational lessons that informed subsequent planning. But the gap between the response posture that currently exists and the response posture that a Sinlaku-level event requires is not a gap that planning documents alone can close. It requires physical, pre-positioned resources. It requires logistics contracts. It requires the kind of sustained federal attention and investment that the Pacific territories have consistently struggled to command against the competition of continental priorities. There is a structural reason for this that goes beyond geography and beyond budget politics, and it is the reason that connects the infrastructure story, the climate science story, and the military story into a single, larger narrative about American governance of its Pacific territories. The residents of Guam and the Northern Mariana Islands cannot vote in federal elections. They have a non-voting delegate in the House of Representatives. They have no representation in the Senate. They are American citizens who pay into federal systems, who serve in the federal military at remarkable rates. Guam's per capita military enlistment is among the highest in any American community, and who are subject to federal law in all its dimensions. But they have no voice in the federal electoral system that determines who controls the appropriations committees, who sits in the White House, who makes the decisions about where federal infrastructure investment goes. This is not a partisan observation, it is a structural one. The political incentive to prioritize infrastructure investment, disaster preparedness, and climate adaptation in communities that cannot deliver electoral votes is, by the basic mechanics of democratic politics, lower than the incentive to prioritize those things in communities that can. Every politician knows this. Most of them, if pressed, will acknowledge it. And the result is visible in the infrastructure ledger that Sinlaku opened on Guam. In the aging power grid, the vulnerable water system, the hospital that should have been rebuilt years ago, the coastal infrastructure designed for a climate that no longer exists. The comparison to Puerto Rico is instructive and uncomfortable. Puerto Rico is a U.S. territory with a similar lack of presidential voting rights, a similar structural underrepresentation in the federal political system, and a similar history of inadequate federal infrastructure investment. When Hurricane Maria struck Puerto Rico in 2017 as a Category 4 storm, the catastrophic inadequacy of the island's power grid, deteriorating for years under the weight of debt, deferred maintenance, and insufficient federal attention, was exposed in ways that shocked the continent. The death toll, initially dramatically undercounted, was later estimated by epidemiological studies to be in the thousands. disproportionately attributable not to the direct wind damage of the storm itself, but to the extended power loss that disabled medical equipment, disrupted medication supply chains, and left medically vulnerable residents without the life support infrastructure of a functioning modern community. The lesson of Maria, applied to Guam, is precise. The specific failure mode that turned a severe but survivable hurricane into a prolonged humanitarian catastrophe in Puerto Rico. The fragility of an aging, inadequately maintained, under-hardened power grid in a U.S. territory exists in directly analogous form in Guam. The grid failures are not identical in their specific, technical dimensions, but the structural story is the same. A U.S. territory with power infrastructure not built for the storms its geography delivers, in a political system that has consistently under-prioritized the investment required to change that. The people of Guam have been making this argument with increasing urgency for decades. Indigenous Chamorro activists, elected officials, community leaders, military veterans, across the political spectrum of the island, across its various communities and constituencies, there is a consistent, long-standing, deeply felt articulation of the inequity of being American citizens without American political representation, and of the specific material consequences of that inequity in terms of federal investment in the island's resilience to the threats that its geography makes inevitable. Sinlaku is not the first storm to make this argument. Paka made it, Pongsona made it. Every major typhoon that has struck Guam and been inadequately prepared for and inadequately responded to by the federal government has been making the same structural argument. The question is whether the argument is ever heard loudly enough in the right rooms at the right time to change the calculus. And there is the military dimension of this argument, which operates on a different register but leads to the same conclusion. The United States military has been investing heavily in Guam's infrastructure, but primarily in military infrastructure, Camp Blas, Anderson Air Force Base expansion, naval facility hardening. The military construction program on Guam is large, serious, and driven by a clear-eyed strategic assessment of the island's importance to the Indo-Pacific force posture. What the military cannot do, what is outside its mandate and its legal authority, is build the civilian infrastructure that the island's residents depend on. The power grid, the water system, the hospital, the road network, the housing stock. The result is an island where the military facilities are being hardened to increasingly demanding specifications, while the civilian infrastructure remains vulnerable to the same storms that the military hardening is designed to withstand. These are not separate risk management problems. They are the same problem. An island whose civilian population is devastated by a typhoon is not a functioning military operating base. The military's operational posture depends, in fundamental ways, on the civilian community that surrounds the bases, on the local workforce, the supply chains, the utilities, the services that make military basing in a populated community possible. The strategic investment in military hardening on Guam, if it is not matched by equivalent investment in civilian infrastructure resilience, is a strategic investment that is vulnerable to exactly the event that Sinlaku represents. The bases may survive with their structures largely intact. The community around them may not. And base in the middle of a humanitarian catastrophe requiring its own resources to respond to the civilian emergency rather than projecting force into the Indo-Pacific, is a base whose strategic value is temporarily negated by the same event it was hardened to survive. This is the argument that the Guam legislature, the Guam governor's office, and the island's non-voting delegate to the House of Representatives have been making to the Pentagon and to Congress in various forms for years. It is an argument that has found increasing traction within parts of the military's own planning apparatus. In the Indo-Pacific Command's Climate Vulnerability Assessments, in the Department of Defense's Climate Adaptation Plans, in the internal conversations about what it actually means to maintain a forward operating base on an island in the most active typhoon basin in the world in an era of accelerating storm intensity. Sinlaku is putting that argument in front of the decision-making apparatus of the United States government with an urgency that documents and hearings cannot produce. It is making the case in the language that natural systems speak, the language of physics, of wind and water, and the release of energy stored in a warming ocean. And that language, whatever its cost in human terms, has a clarity that no policy paper can match. The broader warning that Sinlaku represents, the one that extends beyond the specific storm, beyond Guam, beyond the Western Pacific, is this: the conditions that produced this storm are not aberrations. They are the new operating environment, the combination of historically anomalous ocean temperatures, elevated atmospheric moisture, and the atmospheric circulation patterns that allowed rapid intensification to proceed without interference. These are not conditions produced by a temporary alignment of random variables. They are conditions produced, in significant part, by a climate system that has been systematically altered by a century and a half of industrial greenhouse gas emissions, and that is continuing to change in directions that make events like Sinlaku more probable and more severe. Every populated coastline in the tropical and subtropical Pacific is now living in an era where the extreme events that the infrastructure was not built for are arriving with increasing frequency. The Western Pacific Typhoon Basin, the Indian Ocean Cyclone Basin, the Eastern Pacific Hurricane Basin, all of them are warmer. All of them are producing more intense storms with greater rapid intensification potential. All of them are intersecting with coastal populations that are larger and more urbanized than they were when the current building codes and infrastructure standards were written. Guam is not the only place where this warning is being written. It is the place where the United States government has the most direct and unambiguous obligation to read it. Because the people in the path of the storm are American citizens, and the territory being tested is American soil, and the political and strategic stakes of failing to respond are, in the current geopolitical environment, higher than they have been in decades. Conclusion: when Sinlaku finally passed, when the eye wall crossed the island and moved northwest, and the winds began to diminish, and the first reconnaissance aircraft and military flights were able to assess the damage, the images that came back were the images that people who study these systems know in the abstract to expect, and that never fully prepare you for the reality. Entire neighborhoods of the kind of mid-century concrete block construction that forms the backbone of residential Guam, stripped of their roofs as if the buildings had simply been opened by a giant hand. The waterfront areas of Hagåtña, the capital, the center of Guam's civic and commercial life, inundated to depths that placed the waterline several feet above the doors of buildings, that the surge had entered and emptied of everything that was not fixed to the structure. Road networks buried under the kind of debris field that makes the difference between a neighborhood and an obstacle course. The brilliant, ancient banyan trees that line Guam's avenues and provide shade to the market areas and parks of the island's communities. Trees that have survived every typhoon in living memory, broken, some uprooted, some standing but leafless, stripped to their structural skeleton by wind speeds they had never experienced, and the power was out, island-wide. As it had been in every previous major typhoon, because the grid was not built to survive this and had not been rebuilt to survive it. And now the question of rebuilding it, again, the same question that Paca had asked in 1997 and Pongsona had asked in 2002, was back on the table with the same answer required and the same budget pressures and the same political distance between the people who need the funding and the people who control it. The recovery from Sinlaku will take the form that recoveries in Guam always take. Slowly, with extraordinary community resilience and mutual aid, with the formal and informal networks of a tight-knit island society filling the gaps that federal systems are too slow and too distant to fill. The Chamorro concept of inafamaolek, roughly translatable as interdependence, the obligation to restore harmony and balance through caring for one another, has carried Guam through every typhoon in its history, and will carry it through this one. The people of the island are not fragile. They are not victims in a passive sense. They are a community with deep roots and deep competence in surviving what their geography delivers. This resilience is worth pausing to honor specifically, because it tends to be both deeply admirable and, in the political calculus of federal disaster response, subtly counterproductive. Communities that demonstrate extraordinary self-sufficiency and recovery capacity in the aftermath of disaster sometimes find that their demonstrated resilience becomes an argument, never stated openly, but present in the budget decisions that follow, for why the level of federal pre-investment in their preparedness does not need to match the level of investment directed at less resilient communities. The logic, insidious in its operation, runs: they managed before, they will manage again. The marginal return on hardening investment here is lower, because the community has shown it can absorb the blow. It is a logic that rewards suffering with reduced future protection. It is a logic that the people of Guam have been navigating, with frustration, with advocacy, with the particular political creativity required of communities whose formal political leverage is limited, for generations. But their resilience should not be mistaken for evidence that the situation is acceptable. The resilience of a community in the face of repeated, severe, inadequately prepared for disasters is not an argument for leaving the preparation inadequate. It is an argument for the moral seriousness of the obligation to do better. The United States has that obligation. It has it because Guam and the Northern Mariana Islands are American territory, and their residents are American citizens. It has it because the strategic importance of these islands to American security interests in the Indo-Pacific is immense. It has it because the science of what the climate system is doing to the typhoon environment of the Western Pacific is unambiguous in its direction. And it has it because the gap between the infrastructure these islands have and the infrastructure they need has been documented, argued, funded partially, and closed insufficiently. Not because the problem is unsolvable, but because the political attention of the continental United States has consistently been focused elsewhere. Sinlaku is not just a typhoon. Every typhoon at this scale is a referendum on what a society has decided its obligations are to the people and places in its territory. Every major typhoon that strikes an inadequately prepared island with inadequate infrastructure and inadequate federal response posture is a statement, not an intentional one, not a statement that anyone chose to make, but a structural statement nonetheless about where those obligations rank against other priorities. The statement that Sinlaku made is legible. The ledger is open. The evidence of what was built and what was not, what was hardened and what was left vulnerable, what was invested in and what was deferred, is visible to anyone who wants to look at it with honest eyes. The question is whether it will be read. Not in the immediate aftermath, when the cameras are there, and the federal officials are making statements, and the emergency declarations are signed, and the disaster assistance funds begin to flow. In the aftermath, everyone reads it. Everyone responds with the appropriate urgency. Everyone commits to doing better. The question is whether it will be read 6 months from now, a year from now. In the appropriations hearings and the military construction budget requests, and the federal infrastructure program, authorizations, and the climate adaptation investment decisions that will determine what Guam looks like when the next Sinlaku arrives. Because the next one will arrive. The science does not say when. It says that the conditions that produced this one are not going away, that the ocean is warmer than it was, and getting warmer, that the rapid intensification events that made Sinlaku what it was are becoming more probable, that the tail of the distribution, the extreme end, the record setters, the storms that exceed what the infrastructure was built for, is getting fatter. The next Sinlaku is already somewhere out there in the warming Pacific, waiting for the right combination of ocean heat and atmospheric alignment to be born. It is not a prediction of a specific storm on a specific date. It is a statement about the system, about what the physics of a warmer ocean and a more energized atmosphere have made possible, and what they have made probable over the coming years and decades. 160,000 American citizens live in Guam, 50,000 more in the northern Mariana Islands. They live there permanently, fully, completely, raising families, running businesses, serving in the military, paying taxes, building communities. They are not transient. They are not visitors. They are home, on American soil, in the most intense typhoon basin in the world, in an era when that basin is producing storms more powerful than anything in the instrumental record. They deserve a federal government that reads the warning. They deserve infrastructure built for the climate they are actually living in, not the one that existed when the building codes were written. They deserve a disaster response posture that matches the scale of the threats their geography imposes on them. They deserve political representation commensurate with their citizenship and their military sacrifice and their strategic importance to the country whose passport they carry. And they deserve to have the rest of America, the continental America that rarely looks west across the Pacific to where the real exposure is. Pay attention. Sinlaku announced itself with the physics of the most powerful kind of storm the Earth is capable of producing. It announced itself in satellite imagery that went viral among meteorologists and was essentially invisible to the broader American media. It made landfall on American soil, and the coverage on the continent was a fraction of what it would have been for a storm of equivalent intensity striking the Gulf Coast. That asymmetry is not a judgment on the goodwill of the continental public. It is a function of the same structural reality that shapes the infrastructure investment and the federal response posture. The Pacific territories are at the edge of the American cognitive map, and the edge receives less attention than the center. There is a specific irony embedded in that asymmetry that is worth naming directly. The United States spends billions of dollars projecting military force into the Western Pacific, precisely because it has assessed that the region is critical to American strategic interests. It maintains forward bases on Guam explicitly because being present in that part of the world, at that distance from the Asian continent, matters enormously to what the United States can do and prevent in the geopolitically most contested region on the planet. The argument for that presence, the argument made in congressional appropriations hearings and defense strategy documents and think tank publications year after year, is that the Western Pacific is central to American security. It is not peripheral. It is not an afterthought. It is among the most important geographic domains in American strategic planning. And yet, the 210,000 American citizens who make that forward presence possible, who provide the workforce, the community, the civilian infrastructure that makes military basing viable, are treated in the attention economy of the continental media and the political prioritization of federal budgets as if they are exactly that, peripheral, afterthoughts, people whose storms become news briefly and whose recovery becomes invisible quickly. Changing that is not a meteorological problem. It is a civic one. It requires the continental United States to extend its sense of what America is, to update the mental map, to feel the typhoon warning for Guam the way it feels the hurricane warning for Miami, to understand that the American citizens watching the water rise on the western coast of a Pacific island are owed the same concern and the same urgency as the American citizens watching the water rise in any other city on any other coast. The storm that just hit Guam was stronger than almost anything else on Earth. It hit American citizens on American soil, and almost no one was watching. That is the warning, not just from Sinlaku, from every extreme typhoon that has hit the Pacific territories of the United States and been met with inadequate preparation and inadequate attention and inadequate follow-through. The warning is patient. It repeats itself, each time a little louder, each time with a storm that is a little stronger than the one before it, each time with a ledger that shows a little more clearly the cost of not reading it, each time with a community that recovers through its own extraordinary resilience and then watches the federal attention dissolve and the infrastructure remain unchanged and the next storm season begin. The physics of what is coming will not wait for the political calendar. The ocean does not pause its warming while Congress debates the budget. The storm that will follow Sinlaku, not this year, perhaps, but in the years ahead, in the decades of a warming Pacific that will produce events like this with increasing frequency is already implicit in the temperature of the water and the instability of the atmosphere, and the direction of the trends that climate science has documented with meticulous, peer-reviewed, reproducible precision. The Western Pacific is warming. The storms are intensifying. The people in their path are Americans. It is time to start watching. It is past time.